Now, at this point, I'm going to tell you about something that happened just a few lectures ago in Lecture 3. In Lecture 3, if you remember, we were talking about dissolving stuff, mixing stuff. And I spent some time looking at the idea of dissolving gases in water, liquids in water, solids in water. And suddenly I'm right back here as we look at solubility of salts, talking about some of those same sorts of ideas. Well, what were some of the general guiding principles that I developed in that lecture? One of the guiding principles was the simple notion that like dissolved like. That if you put stuff that was polar in the vicinity of stuff that was polar, it would dissolve in it. If you put stuff that was nonpolar around nonpolar stuff, it would be miscible with it. On the other hand, if you took stuff which was polar and put it with stuff that was nonpolar, like oil and water, they would not be miscible. They would not be soluble. That allowed us to predict things like the fact that polar sodium chloride and polar water would have a tendency to be able to dissolve in one another. On the other hand, things like naphthalene and toluene, very similar looking non-polar compounds, they would tend to be miscible with each other. But I'm not going to be able to mix sodium chloride and naphthalene and toluene. I'm not going to be able to mix naphthalene and toluene in water. So that was my like versus like kind of argument. The other argument that I developed that was specific to salts had to do with this simple idea here. Because salts are made up of charged particles, and those charged particles have simple sorts of guidelines in terms of what their charge is like based upon where they sit in the periodic table. There's my first row with the alkali metal ions. Those are +1 as salts, as ions in terms of trying to satisfy noble gas configuration. My halogens are -1 in terms of trying to satisfy noble gas configurations. It allows me to pretty quickly identify a couple different categories of salts. The singly charged salts like alkali metals and the halogens, and the multiply charged salts like calcium ion or aluminum ion or oxide ion or sulfide ion. Well, when you think about trying to take a single positively charged ion and negatively charged ion and put them together, you realize that the lattice energy associated with this attraction that we have here like that, just isn't going to be nearly as strong, nearly as much glue as when I have a +2 and a -2, or a +3 and a -2 coming together, and their lattice energies are much higher. As a result, I have this nice simple rule of thumb which says that singly charged species typically tend to be the sorts of things you can rip apart more easily than multiply charged species. And while the rule of thumb for this is not absolute, and there are lots and lots of exceptions, it did allow us to say, well, what do you know? Potassium ion, sodium ion, nitrate ion, ammonium ion, singly charged. Is that a coincidence? They all dissolve in water. Carbonate ion, sulfide ion, phosphate ion. What do you know? They are multiply charged. They don't dissolve in water. So while there are exceptions, it's kind of nice to be able to talk about this general sort of rule that keeps us from having to memorize the solubility rules. Instead, let's just walk away with this kind of passing knowledge that says that every time you see an alkali metal ion, you know that stuff is soluble in water, no matter what it's attached to. And every time you see a halogen, for the most part, you say, yeah, that's going to dissolve in water, regardless of what it's attached to. And everything else, probably not. And that's what we know up to this point about dissolving salts in water. Notice it's all qualitative. There's no number associated with it at all. Now, when I talk about throwing chalk into water, calcium carbonate, I say, that's not very soluble. How do I know that? Well, because when I throw chalk into water, and it sinks to the bottom as a piece of chalk, and I come back 2 days later and it's still a piece of chalk on the bottom, I would imagine that not very many of the calcium ions and the carbonate ions went up in the solution. I know some of them do because that's how we get water hardness. That's how we get pipes that get clogged. On the other hand, I can take sodium and chloride ions and I can dump them into water, and I know that they dissociate a lot in water because I take a sip of it and I go, whoa! That is really salty. The point here, though, is I am tired of having to say, that's not very soluble, or, boy, that's really soluble. I'm going to replace that instead with math, with numbers. I'm going to tell you that there is a single number out there called the KSP, and that number by itself is sufficient to tell you just how soluble a compound is in solution, because that number tells you how much dissociation of salts into ions has actually occurred. And knowing KSP means you know these values here, which means you know exactly how soluble your salts are. Not pretty soluble, but 10 to the minus 2 molar soluble. Not really, really, really soluble, but 0.1 molar soluble.